Hello, everybody. Today I'm going to be discussing X-ray diffraction applications for metal additive manufacturing. My name is Calvin Thomas. So what is additive manufacturing? It is a newer method of manufacturing which is able to output more complex and sophisticated products of varying materials. Additive manufacturing uses heavily integrated computer systems and software to turn designs into tangible objects. Additive manufacturing is the opposite of subtractive manufacturing. Now, subtractive manufacturing includes processes such as milling or stamping. Any process that takes a piece of material and removes parts until a desired product is left is considered subtractive manufacturing. Now, additive processes build material up, which saves resources. So additive processes have become much more accurate and precise in recent years. They also are universally practical because they don't need casts, dies, molds, or more cumbersome equipment, such as hydraulic presses and other large equipment of that nature. However, the technology is relatively young in comparison to the traditional methods of manufacturing. So the processes are still being perfected and new innovation comes each year. Now, a little bit on the history of additive manufacturing. The general concept came out in about the 1970s or so. However, it's not heavily experimented upon until the early 1980s. Dr. Hideo Kodama began studying and experimenting with laser curing for rapid prototyping. His research and work in additive manufacturing would be the foundation for stereolithography. Dr. Hideo Kodama was the first person to apply for a patent as well for laser beam resin curing. However, he was unsuccessful due to funding issues. Soon after, a team of French engineers attempted to continue his research in stereolithography. Jean-Claude André, Olivier de Witt, and Alain de Mahat were attempting to find a method for creating fractal objects. Now, fractal objects are objects that have patterns identical to the whole of the object. So any given part of the object is the same as the entire object. This is a very intricate and complex design for an item, something that requires a lot of time and repeating patterns. So the French team concluded that stereolithography, or a method of that nature, would be a good avenue for performing the manufacturing of this type of object. Although once again, the patent for this fell through because of funding issues in 1984. Now, for those unfamiliar with stereolithography, it is a process in which a light-sensitive resin is solidified with light. So this sort of technique would be the basis for many early additive processes. Photopolymers would be the material of choice for this type of process. The way in which it works starts with a basin of photosensitive resin that is struck with a high-intensity laser, which then forces the material to harden. And then after that, a new layer of liquefied resin is added on top in a very thin manner, and then this is struck again by a laser, which then again hardens it. This process is repeated over and over, going layer by layer with very small thicknesses until the final part is created. Now, there's a platform beneath the resin basin that adjusts to each new layer of resin, so it moves down as the parts are solidified into its final shape. After some elementary research and experiments with stereolithography, another man would come to fabricate machinery capable of applying this method. Charles Hull was an inventor previously familiar with photosensitive materials from his previous job, curing tabletop resins. So Hull would utilize UV light to harden the table's coating, which then prepared it for sale. Now, using the similar technique, he was able to mimic that for stereolithography. In 1986, he filed for a stereolithography patent and went on to found 3D Systems in California. This company now produces 3D printers and 3D printing materials, scanners, and other 3D printing services. But Charles Hull's work with stereolithography pushed the technology of additive manufacturing into the view of manufacturers, making the additive process a subject of innovation for inventors. After this point, however, more inventors and manufacturers began investigating other methods for additive manufacturing to expedite prototyping times. So the bottom left image that you see here is the first stereolithography machine. So it takes a digital design, and then we'll turn that into a three-dimensional object made out of the resin. So this was Charles Hull's first prototype for that. In 1988, however, Carl Deckard conceptualizes and patents another additive process known as selective laser sintering, or SLS. This process uses a bed of polymer powder and a laser to sinter grains together. Now, sintering is somewhat similar to melting, but it's a little different. Sintering brings the material to a temperature enough for fusing particles, but not enough to fully melt it. So this saves energy and makes the material a little easier to control, because if it's liquid, it might run or move around a little more. But if it's not fully liquid, it won't move as much. Now, simultaneously, another man named Scott Crump from Stratasys Incorporate patented the fused deposition modeling method for additive manufacturing. This process is what most people now know as extrusion printing, which many modern day commercial 3D printers use this type of method because it works well with polymers. As the 1990s approached, more innovation occurred, further improving these processes. The industrial manufacturing industry turned to additive manufacturing for new ways to rapidly produce intricate products. The Fraunhofer Institute built upon the SLS, the selective laser sintering process, using a newer, slightly derivative method called selective laser melting, which only differs to sintering by fully melting the target area of the powder bed to fuse it to other particles. This would prove useful in some heavier duty applications. Application of the previous methods of additive manufacturing towards metals culminated in the direct metal laser sintering process, which was invented in 1994 at Electro-Optical Systems in Germany. This method is very similar to the selective laser sintering, as you can imagine. However, it relies on much stronger lasers and a bed of powdered metal rather than powdered polymers. Direct metal laser melting is a deviant of sintering method, as we previously discussed. It usually is dependent on the material being used, however, if you're going to do sintering or melting. Some metals that have much higher melting temperatures, you're going to use sintering. And then those that have lower melting points, you might use the melting method instead. Now, the machine responsible for this method starts with a powder bed that is very thin upon ignition, similar to the other methods that we've already discussed. And a laser is directed and aimed towards the bed where it can sketch the design of the desired part. Once a single pass through of the two-dimensional cross section is done, an arm sweeps over another very, very thin layer of powder over the printing bed, where the laser will then trace again the next layer of the part. This will repeat until fully finished. Now, around the same time, however, the electron beam melting process was birthed as well. This additive process follows similar structure, yet instead of a laser, it's an electron beam. And that is also used to etch the design into the powder bed, heating the material until it melts. So essentially the same idea as the laser melting method, although it's electron beam instead. And the electron beam itself is directed and focused using magnetic coils and other methods like that. There's no lenses. It's usually through magnets or electromagnets to do so. The melted layer solidifies, and then the next powder layer is deposited where the beam repeats the design again. So to briefly sort of visualize this method, I'm going to show a quick little video, which could allow you to better understand. But the laser will etch the design, and then the platform moves down a little bit, and an arm will sweep over a new layer of the powder, where it then continues until it's finished. So it's very, very blank canvas, but it's a very good way to make these very intricate parts and small parts as well. Overall, however, metal additive manufacturing is a wonder of advanced manufacturing. It provides plenty of advantages compared to molded metallurgy processes, So this additive process is more resource efficient as well. There's a lot less that's wasted with each product produced, and it has much more accuracy too. So the computer that's controlling the machine is very, very precise in essentially directing where the laser goes or where the electron beam goes, rather than some sort of heavy machinery that might be manually operated. And this will allow for the dimensions and designs to be much more of what the digital copy of the design might be. So for example, here, the heat sink on the right is a great example of something made by metal additive manufacturing. So as you can see, it's incredibly intricate, a lot of little turns and tiny little details, but this additive process doesn't struggle making products like these. So overall, like, the entire process is also much safer as well compared to molding or casting of metal parts, which require, heavy duty forges for molten metal, big presses and large machinery. This also means there's less power utilized for transforming raw material into metal parts. And then finally, the turnaround rate for an additive process is quicker than that traditional methods. There's less cooling times, which makes it just quicker in general. Now, X-ray diffraction plays a valuable role in making sure that additive manufacturing can be optimized for part quality. Typically, X-ray diffraction is used to identify the phase of a material by mapping the intensity of a received ray of X-rays from the incident X-ray. The angle is varied during the experiment, such that a plot of the Bragg angle and the received intensity can be made. Now, this plot is known as the X-ray diffraction pattern, which is unique to any given compound. This helps scientists and engineers identify the sample substance, and it can even help to determine crystalline structures of the sample on the atomic level. The benefit of using this process over a chemical one is that it's faster and quicker, and it's also a non-destructive way for identifying the material. If we had to use a chemical process, something would react with the sample and inherently changing it where it's no longer usable. So this is a good process because that doesn't happen. Once the material goes in and comes out, it doesn't really change at all. In the case of metal additive manufacturing, we commonly see that metal is crystallized in all sorts of phases, which results in different properties of the metal. The cooling routines for a process differs from that of, say, any other sort of additive process of the same family. So the cooling stage causes a lot of variations in the grains of a metal. Controlling this phenomenon is very difficult, but it's crucial. It's important for the process. For example, a larger grain can lead to more weaknesses in the sample, which can cause failures in the manufactured part. Nobody wants that. The producer or the consumer do not want parts that are going to fail at unexpected places or after an unexpected amount of time. The orientation of these grains also determines certain mechanical properties, which is detrimental to making parts for applications that provide exposure to very harsh conditions, such as airplane or industrial parts for factories, anything that might see high temperatures or high fluctuation temperatures, and then fluctuation in strains and loads and stresses. So the way in which X-ray diffraction will help this is by characterizing the X-ray diffraction patterns of the sample and comparing them to the nominal patterns of the material. If there are discrepancies, then something could be up. Grains could be different than normal, impurities can be present, list goes on. Using the Scherer equation, we can determine the crystallite sizes by knowing the angle and wavelength of light. Whatever the desired crystallite is can be compared to the experimental. Once again, if there's a discrepancy, changes to the substance can be made to correct these issues. Another application for X-ray diffraction in metal additive manufacturing is through liquid dynamics of the metal sample. So observing how the metal solidifies or sinters during the process is valuable in understanding if the process is producing quality parts. So the way in which this is done is called in situ growth observation. So the sample of an X-ray diffraction experiment will be liquid or maybe partially liquid. And as it solidifies, the pattern is tracked over time. So for example, the plot on the right shows a typical X-ray diffraction with another dimension of time involved. So we can see as this is cooling and crystallizing, the Miller indices are apparent. Now this allows for scientists to see if crystals are forming properly, if there's some sort of deviation in what we expected, or if somewhere along the way an extra indice pops up and then comes down, maybe something's up there. Typically though, if impurities are present, cooling times are different as well, which is something we can track as well. And microstructures could be altered too. Now, X-ray diffraction can also be applicable with simple quality assurance or quality control. When parts are being made, it is very important to make sure that the material used is as pure as desired. This will stop parts from the additive machines from being damaged. So frequently in extrusion-based machines, impurities can be catastrophic for the dispensing equipment. An impure substance will have a different melting point, usually, compared to the rest of the sample, which will result in some hiccups in the part. X-ray diffraction can make sure that engineers can identify contaminated material beds and aid in material selection process too, to make sure the printing process goes as planned. In conjunction with this, post-production quality control is an area that X-ray diffraction can be helpful in. Observing the X-ray diffraction patterns of a finished part can help manufacturers see if crystals form properly and if grains are desirable size. Knowing this helps know if failures are likely to happen too. Residual stresses are not desirable happenings in samples either, which is why X-ray diffraction is used to identify them. When an X-ray diffraction pattern is assessed, peak shifts can insinuate a change in the crystal lattice parameter of a crystal size in general. This could potentially imply an impurity in the substance or faults and dislocations. Assessing the textures is also something that X-ray diffraction can detect. So when crystals are oriented in certain ways, they create a specific texture on the atomic level. Now, a texture could cause deviations in the expected diffraction peaks seen during an experiment. So it's important to compare what you got in the experiment to what's expected, or what are the nominal X-ray diffraction patterns. So overall, X-ray diffraction is very relevant and important in metal additive manufacturing. Benefits to consumers and manufacturers are pretty apparent. The more assessment that's done on the material allows for higher quality of the parts. On top of that, it also saves money and energy when you use the correct materials. There's less errors, there's less redos. A part printed is always going to be a part sold. There's no excess waste or surplus. This also makes additive manufacturing a better option for producers. Again, there's less mistakes and issues all around. You have higher quality products, which looks better. So thank you for listening. If you have any questions, please leave some comments in the discussion page, and I'm happy to answer them. And I look forward to your comments. Thank you.